tonight I will talk about reconfigurable computing and how this could be used for scientific computing and data analysis. And so this is a topic that has been kind of recurring in our discipline in HPC. There have been attempts to use FPGA or reconfigurable computing in HPC systems many years ago, and they come back with a certain cycle of years. And so today I just would like to go back to this idea, FPGAs for high-performance computing, and try to explain why this may be the good time to do that now. So that's that you will see that there will be some good news in my talk. You will see some impressive number, I hope. But you will see also that it's difficult. It's not prime time for that technology yet for HPC. And so there is still some research needed. And I think that's why it's very exciting. It's because there is something to do, and we can contribute to help make that happen. So I will follow this very simple summary. First thing is, and I think the main motivation behind trying to use reconfigurable computing is the end of Moore's law. So you have heard about this word, and I will just detail a little bit more to explain why it could be the foundation for the adoption of reconfigurable computing. And then I will explain 4 trends toward what I call tailored computing or tailored hardware, which is in fact just the use of FPGA in HPC. And so I will explain 4 different points that I think are very important toward the adoption of this technology in our domain. And then I will spend a few slides showing the current applicability of FPGA and how we can use them in some applications. And so this would be the good news. And I will finish by news which is not that good, but I think that will open new opportunities for research, which is a reality check. So we have tried things, and I will just express what we have learned so far. And you will see that it's something not easy these days to do that. So I think everything on FPGA for HPC today, the foundation of that is the end of Moore's law. So if you look at this diagram, you probably have seen them already. So what you see here is the usual expression of the Moore's law, which is that you double the number of transistors at a constant cost every 18 or 24 months in the circuits that we use in our systems. Okay, so this was an observation that has been made back in 1965 by Moore. And so if you look at the trend, this is 5 decades of Moore's law that we had. And this is due to the CMOS and the technology and how the technology was improved across these different decades. And this was the main factor behind the improvement of performance in HPC and in general in the IT domain. The Moore's law is really very, very important for the increase of performance in general in computer and computer science. But the problem is that it's more and more difficult to keep up with this exponential increase of the number of transistors. And if you look to the ITRS projection, which is the roadmap made by the people who built the circuits, if you look at the projection, they are printed here. You see the projection for the gate length, which is the size of the transistor, the one you hear when you are talking about a processor that is in, 40 nanometers technology. So this is the length of the gate of the transistor that we are mentioning when we are talking about that. And so here what you see is how the length of the transistor of the gates will reduce according to the years as projected by the ITRS. So what's interesting in this graph is not to see that we go from 25 nanometers to 5 nanometers. Today we are at 14. It's not that which is interesting in this graph. Which is interesting is that on the same graph, you have the projection done in 2005, in 2008, in 2011, and 2013. And the observation is we are delaying the new technology. We are delaying significantly by 5 years the apparition of the new technology, next one, okay, the one that will provide a better processor or faster processor. And if you look at the situation here, you see that 5 nanometer was projected for 2021. It's now projected for 2027. And in fact, if you talk to some people in the industry, they may tell you that, in fact, it will never happen because it's too expensive to build the factory to construct the device at that definition. So it's very, very difficult to keep up with the Moore's law. And as I said, the 5 nanometer may not happen. So if you then look at what does it mean for CMOS, so the technology that we are using in our system, well, the density will be bound. So this means that you will have a certain number of transistors per surface unit, and this will stay the same. You will not be able to put more transistors in the same surface. So this will be a given factor. So how you can still improve the performance of your system? So you may try to use the third dimension. So if you look at the circuits, it's two-dimensional. The Moore's law happened to increase the number of transistors using an exponential factor because you were also shrinking the dimension in the, of the transistor in the two directions. Now you only have one dimension to play with, which means that it will be much harder to keep up with the progress. So it's maybe the exponential time is over. Okay, maybe we will have a linear progress in the number of transistors that we can have in a circuit. But at some point, if you start stacking the circuits in 3 dimensions, so that's the third dimension, you start stacking the circuits, right? At some point, there will be a limit too, right? You will have a power limit. You will not be able to bring the power to all this stack, or you will have a heat limit. You will not be able to remove or extract the heat from this stack. You may have some testing limit, very difficult to test these 3D stacks of ICs. Or there might be a cost problem. Building 100 or 1,000 layers of ICs like that in 3 dimensions may be very expensive. And if you look at kind of urban theory, at least at if you look at Wall Street, no tree grows to the sky, and I think we can pretty imagine that you cannot build, circuits very tall to try to put as much as transistor as you can. So there will be some limit here in the progress of CMOS, even if we exploit the third dimension. So we have to look at the situation of what will happen if the number of transistors is bounded, if the frequency is bounded, and this is already the case since almost 10 years now, and if the power is bounded, okay, if you have a limit of power. So if all these factors are bounded, how you can still increase the performance? That's the question that we want to ask. So we see at least 3 directions. So the first one is, of course, what the big company like Intel or Samsung are trying to push as much as possible is to find new technologies. Okay, so you can find here very exotic things like nanoscale vacuum channel transistor. So these are the vacuum tubes, but in the nanoscale. Very interesting technology. Spin devices, Josephson junctions that work at a very low temperature, or carbon nanotube. So there was Subhatish Mitra at MIT who showed a first processor built with this technology, carbon nanotube. He had 178 transistors. Okay, this was 2 years ago. We are very far from billions of transistors that we have now in our systems, in our processors. So you see that there are some effort to try to bring new technology, but there is first, it seems that they will not be ready before the end of the decade 2020. And the second thing is that it's not clear that this technology will give us these decades of exponential progress. Okay, so it's really bad news. It seems that the end of Moore's law is very, very significant and very difficult to address, at least at the technology level. So then you have two other directions. One is to design specialized system. And you will see several slides about that. This is something that the HPC community has done in the past. You build a system, specifically for the application that you have, that you want to run, okay? And this will serve only this application. And you design the hardware for that. So if you want to improve the performance, you will need to design a new hardware, which is very expensive. Okay, so that's the specialized architecture, and that's also a very well-known notion of co-design. You co-design the application, the system software, and the hardware to build this system. So you will see two examples of them in the next slides. So that's specialized architecture. And there is something, probably you have guessed already, which is not exactly a specialized architecture, but it's not a generic processor neither. It's reconfigurable design, okay, reconfigurable architecture. And that's a way that we can try to exploit or to explore and see if we can, from this design, this approach, get the performance increase that we want. So there are several companies working in reconfigurable computing. The most known ones are Altera and Xilinx, and you will see some of the devices provided by these companies. So let's talk about specialized architecture. One famous specialized architecture is the Anton 2 machine. It's built to compute molecular dynamics. This has been presented at HotChip 2014. They built the chip is there, okay, which is dedicated for this application. And what the machine does, what you see the machine here, is it simulates the motion of atoms in biochemical systems. And we are talking about a lot of atoms. We are talking about millions of atoms that we want to put in this simulation. And we talk about time steps that are extremely small, 2 femtoseconds. And a lot of time steps for the simulation, 1 tera time steps for the simulation. So they build a specific chip. It has 66 CPU cores that are very specific. They use fixed point arithmetic. The frequency is 1.6 gigahertz, and it provides 12.7 tera operation, fixed point operation per second, which is very, very nice for a power consumption of 250 watts. And if you compare to the Tesla, so to the state-of-the-art NVIDIA card that you can buy for accelerators, you will have similar numbers in terms of performance in single precision, and you will have also similar numbers in terms of dissipation. But this system is really completely designed for the application, so it's not as general purpose as the Tesla. Okay? The technology is a little behind. You see that it's 40 nanometer. The technology of Tesla is 20, or the K80 is 28 nanometer, and the same year this has been announced, Intel announced the Broadwell processor at 14 nanometers. So there is a shift between the technology that you can use to build your own ASIC, your own special circuits, compared to what the big vendor can do with their fabric, with their fabrication lines. And so what they present in this paper in 2014 is that they can go 2 orders of magnitude faster than a general purpose supercomputer for this specific application. You cannot run anything else on this system. And you see here the node with a big sink heat, which is also a problem. Even for specific design, you have this problem of dissipation of energy. So as I said, specific system is not really new. What you see here is another specific system which was built in Tokyo University. It's called the GRAPE-4. It's a gravity engine. It's made to compute gravitation. And so this was several generations of systems that were built with a time lag of 5 or 6 years between each system. Very, very difficult to build new systems, new specific systems, to get the money to do that and to design all what's necessary to run the system. So it's interesting to develop specific system, but it's very long to develop. It's very difficult to use the latest technology, so you are a little behind in terms of technology. You need to design for a fixed algorithm. This is the algorithm that you want to implement in your system. If you want to improve this algorithm, then you will need to build a new ASIC, a new chip, which is very expensive, cannot run efficiently on other systems. As I said, it's very expensive to build. And so that's one solution. But again, if we are with these limits in CMOS, so even if you do an ASIC, if you reach these limits where you cannot improve you cannot put more transistors, you cannot increase the frequency or the power of these circuits, then you will need to change the algorithm, and then you will need to redesign and to rebuild an ASIC for a specific system. So it's a kind of very difficult track to follow. So now I will talk about reconfigurable computing. I think it's a much easier way to build systems that are tuned for some application and that you can tune for large variety of application. Probably they will not be as fast as a specific system, but they will use the latest technology, and you can expect to get very high performance per watt compared to CPU or GPUs. So the first of the 4 trends, I will present 4 trends now that push toward this reconfigurable computing hardware. The first is that FPGAs are getting competitive in floating point performance compared to GPU and CPUs. You will see that in the next slides. The data is becoming a very important performance constraint in our application, and so developing new mechanisms to address the size of the data, to reduce the size of the data is very important, and FPGA are very well adapted to that. And we can try also to reduce the power and the size of the operator, so to design operator and to put the operator on the FPGA that correspond exactly to the data format that we are using. And this will save, in fact, space. This will save power, and so you will be able to put more of them in a single circuit, and so that's a way to improve the performance. And the 4th trend, I think, which is probably one of the most important ones, is that it's already adopted in data centers. So you already have FPGAs now running in Bing, so what Microsoft is using for as a search engine. So in Bing servers, you have FPGAs that are helping to respond to your requests. So the FPGA are adopted in the industry, not in HPC, but in data centers. And so there is, I think, a path behind that. You will see that there is another industry which is very important that can help popularize the FPGA or help support the FPGA development. I think this will be the main, the main important foundation for the development of FPGA in the future. We'll say that in several slides. So let's talk about an FPGA now, and what I show here is really the state of the art. It's not yet on the market, should be on the market in 2017, beginning of 2017. It's called the Altera Stratix 10. I could have presented another FPGA from Xilinx with some also very nice characteristic. I choose to present one, and this is one from Altera. But it gives you an idea of what we are talking about. So we are talking about SoC. So these are systems on a chip where you have an FPGA fabric that you can reconfigure, but you have also a lot of things around it. In particular, you have 4 processor cores that are here to help computing things that you don't want to compute on the FPGA fabrics, for example. So if you look at this device, in addition to the FPGA fabric and the cores, the processor cores, so ARM cores, you have DSPs. And these DSPs are computing in single precision IEEE, following the IEEE standard. Okay, so you can directly compute in single precision arithmetic using these DSPs. And if you look at the total performance achievable with these DSPs, it's 10 teraflops. So it's comparable to what I mentioned before for the GPUs. Well, same type of performance. But the performance per watt is 3 times better. Okay, it's 100 gigaflops per watt. If you look at the K80 for NVIDIA, it's about 26 gigaflops per watt. So it's much better in terms of performance per watt. So you have these ARM cores, and you have also a connection to the memory, which was the problem for FPGA before, and for their adoption in HPC the problem was not so good connection to the memory. So now this device, you can connect it to a hybrid memory cube, with a total bandwidth, okay, it's split over 64 lines, of 1 terabit per second. Okay? If you compare to a GPU, you will see that it's the same order of magnitude in terms of bandwidth to access the memory. So this device has a performance close to a GPU, at least on paper, right? And a memory interface, which is also very, very good. In addition to that, you have transceivers. So this means that you have communication mechanisms, and you have a lot of them. So here I present just this number, but I think it depends on the configuration of the device. But here you can have, in one of these configurations, you can have 144 transceivers, each with 30 gigabit per second. So if you want to build a parallel computer based on that, you can try to connect directly the FPGA between themselves. So that's something that would be very interesting, very exciting, I think, to do. And of course, it's still a FPGA with 5.5 million logic elements that you can configure for your application. And one thing which is important for this new generation of FPGA is the clock. So the clock now is close to what you can get in the best in CPUs, 1 gigahertz. And this is due to some trick that they use in the fabric itself. Well, there are some other aspects that I will not describe here, but I think the message that I wanted to pass with this slide is that the FPGA that you may have known in the past has very little in common with this type of device, which is SoC with some FPGA fabric, but also surrounded by a lot of other features. And by the way, it's using the same technology, the 14 nanometer, as the one you can have in the best Intel processors. So there might be some connection here because Intel bought Altera recently. Okay, so I mentioned that there are some tricks. They use variable precision DSP blocks. I will not explain that in detail. The hybrid memory cube, I already mentioned that, 64 channel, to bring this performance that I mentioned of 1 terabit per second, which is same order of magnitude, a little lower, but same order of magnitude of what you can get in the K80. And this thing that I mentioned, a trick in the fabric, which is very interesting. Normally, the clock in FPGA is defined by the longest logic chain that you have to cross. And in this FPGA, you can put in the fabric itself, also in the link that you are using to connect logic element, you can put registers. So there are registers in this fabric, and this register will be used to clock and to have a higher frequency on the fabric. So that's how you can have a frequency of 1 gigahertz instead of 200 or 300 megahertz. So that was the first trend, I would say. The FPGA are really becoming interesting on papers. So we need to make some performance evaluation to really check where they are. You will see some of them in some slides. So that's the first trend. The second trend is that we are facing a major problem here in our community, HPC, with the size of the data that we are producing. And if you look at planned experiment, simulation or experiment, some of them generate data that you will not be able to store or to communicate. So many data that you really not be able to store or communicate. And you have two examples of this here. One is the HACC cosmology simulation. Well, so what you try to simulate here is the galaxies, formation of the galaxies, and how they have been formed from the Big Bang. And what they really want is to run a simulation that produces 500 time steps, and they want the maximum resolution on all of these time steps. Today, what they do is that for each time step that they produce, they remove 90% of the information. They just drop 90% of the information, and they get this image of the universe. Okay? What they want is to keep this information. The 90% they remove, they want it. Okay? If they can do that, they will have this picture, which is closer to what we see when we look in the sky. Okay? So they really want to have all this information. But if they run this simulation on 1 trillion particles, they will generate 20 petabytes of data. Well, if you look to the file system of Mira, this is a little bit higher than 20 petabytes. But you will never be able to use the full file system for yourself for just one simulation. And then you will need to move this data away from the file system. This will take a lot of time to put that on tape. Okay, so that's what they want. And because they cannot have that today, they drop 90% of the information that they generate. Okay, so that we have a serious problem here. Another important problem, this is the upgrade of the Argonne photon source. So it's there. There is an experiment, which is the BRAIN initiative. And the idea is to do a high-throughput X-rays tomography of the whole mouse brain and to make a lot of comparison between brains of mice. Okay? And so each specimen will generate 160 terabytes of information, and they want hundreds of specimens. So again, you are dealing with hundreds of petabytes of information. But it's worse than for the case with hack. Here, you need to transfer this information from the APS, the Argonne photon source, to Mira. And the link here is 20 gigabits per second. So if you just do the math, it will take more than 1 year to move this data. Okay? You don't have this time to move this data. And even if you try to improve this link, 100 gigabits per second, that's doable, still you will have a lot of time to move this data. And so that's a big problem. So people are now really thinking about compression, using compression for reducing this data set and try to keep as much as information as possible. And so what I will present here is not an application of compression for hack or for the Argonne photon source. I will just show why compression or how compression works well on FPGA compared to GPU or CPU. So what you have here is a team that published a paper in 2014 about implementing JZip. Well, everyone knows JZip, okay? It's a very well-known compressor. It's lossless compression. 2 stages, LZ77 and Huffman compression, very simple stages. And they try to implement it in FPGA. So this is a team with Altera people. So it's not you and me. These are the people who are designing the circuits. Okay, so they really know how the software stack is working, how the hardware is working. So here you see the performance in terms of performance per watt and compression ratio when you have the FPGA and run on the Intel processor. And I don't know if I have the Intel processor is 1 core at 3.2 gigahertz. And so what you see here is the performance. So the FPGA is about 10 times faster to compress the data. Performance per watt is 12 times faster. Okay, so that's a good thing. In terms of compression ratio, similar. It's normal. It's the same algorithm, right? Now, if you look, you could say, well, okay, so what did they use exactly to program this FPGA? Well, they use OpenCL. So this is not really an extremely low programming level for FPGA. This is a very high. This is the highest programming level that you can have today on FPGA. Okay, so that's very promising. It's a parallel programming abstraction. You can really work with that and put that in the hand of some people who are working in HPC application. So with OpenCL, they get this performance. So the question you may ask is, what would be the performance if really I use an expert of FPGA who really build the FPGA using not the lowest possible programming abstraction, but a reasonable one, so HDL, hardware description language. So if somebody knows how to program in HDL, hardware description language, he will build the circuits to do that. So that's what they did, and that's IBM who did that with Verilog, and with the same FPGA. Okay, so IBM, a different team. Okay, and the performance, well, the paper has been published by Altera, so it's important to notice that. So the gap is 5% in terms of performance. So this means with OpenCL, what they claim is that you can get this performance. In terms of use of logic, this is very important in FPGA. You want to use as less logic as possible, of course. You use 25 more memory, I think, and 2%. 25% more memory and 2% more logic. Okay, so it's a little more expensive in terms of logic. In terms of productivity, of course, programming in OpenCL is what they say 1 month. I will tell you about our experience. I will tell you about that. And of course, if you program in Verilog, it will be months of effort before being able to run something like gzip on the FPGA. Okay, so it seems that there is a point here. So that was the second aspect. If you want to reduce the data, and we need to reduce the data, FPGAs are very nice device to do that. So if we are talking about scientific simulation and data analytics, there is this big data analytics part which is there, and FPGA can help a lot in that aspect. The third point, the third trend is that since we have a reconfigurable device, we can try to use operators that are not standard operators. Okay, so for example, I will use an adder, but it doesn't compute like a normal adder. It will make some errors, okay? But I don't care about these errors because, in fact, I'm not using numbers that will stress the adder and produce this error, for example, okay? And so you have here a large body of research on approximate computing, even at the hardware level, okay? So people have tried to look at different adders, how to program different adders that will have different level of errors, but that will consume much less than the standard adder, which is here. So that's a graph that shows different class of adders. You see here the power consumption of these adders, and you see here the errors that they are making. Okay? So of course, here you can have some very aggressive design that have significant number of errors, I think here, but that would consume much less. And you can look at this graph. I will not detail it, but you have a series of adders, the same that you have here. They compare in terms of density and in delay, and you can see that the normal adder is here for the delay. You can find that you can have adders that will compute approximatively, but will produce a result faster than the normal adder, okay? And with less power, okay? So what this message is that if you can characterize your application in terms of the operand that you will use, you can do some statistic analysis. Maybe you can design an operator which will be tuned for this operation and that will use much less gates than a normal operator will use. Much less gates and much less power, okay? Well, when I hear that the first time, I said, okay, well, so basically what you are telling me is that we are computing and we are making errors. How this could fit in HPC with all the theory that we have on, and the problem that we have with error or quantification of error and understanding even of the error in the numerical methods. Okay, so that's an interesting question. Some people already look at this and tried, and this is just one experiment. I'm not aware about any other, but that's just one. That was done by the team of Krishna Palem. So he pairs with some people who are involved in the development of weather code simulator. Okay, so people who are working in London in atmospheric modeling. And so the idea here was to see if they could design or use a hardware that would produce similar results with a distance between the expected result and the result produced with approximation that would be acceptable for the user. Okay, so these people who were in the team are the user of the code. They are the developer, but also the user of the code. And so they managed to build and design operators. Look, here you have an adder and here a multiplier that use half of the surface. Okay, for the adder it's half of the surface and the power, and here 1/3 of the area and the power compared to the standard operator. Okay, so what they say here is that they would be happy with this type of operator. They will produce results that they can consider accurate enough, okay? But this is a way for them to double or triple the performance or the performance per watt that they get from their device, okay? So if you are completely stuck in terms of you cannot increase the number of transistors, you cannot increase the frequency, you cannot increase the power, there is still something to do here, which is to go into approximate computing or doing exact computing on specific data size. And so I will not explain here, but there is, of course, in bioinformatics, a direct application here of FPGA. You can represent and do genome assembly or alignment sequence and sequence comparison. You can do that very easily with the specific format in the FPGA. And so the FPGA in that domain are naturally fitted, I would say. But I put this here because I think it's an important question for the community to understand if we can really use approximate computing? And if so, then this will help us to improve the performance. So the fourth aspect is, well, FPGA are already used. I mentioned that. Bing, made by Microsoft, tried that in 2014. You can go to their paper and look at it. ISCA 2014. They explain the whole design of what is now running in the data server that behind Bing. And so you have an FPGA that is now a board in each node to perform some operation. And the gain, I think this is for page ranking, the gain is a factor of 2 compared to what if they use a normal CPU. They try to look at GPUs, and what they say in the article is that the power consumption was too high, and it was increasing a lot the cost of ownership of the data center to use GPU instead of normal CPU or FPGA. So there is, FPGA here is a solution to increase the performance and do not increase too much the power consumption or the cost of ownership. And of course, you can say, so why I'm saying that here? It's because to be successful, the FPGA needs to have a support market. Okay, they need to have a very strong support market. And we're not talking about FPGA that we put in sensors. We are talking about high-end FPGA, a board that costs $5,000. Okay, so it's very expensive. They need to have a strong support market to be able to produce this chip in quantity. Okay, and so if there is the data server market, which is behind FPGA, this will reduce the cost, and this will help us adopt this technology. But what I want to say is that there is another market, which is much bigger than this one, which is now looking at FPGA, and this is the autonomous cars. In autonomous cars, you will have high-end FPGA to do all the operation that's needed to drive the car in security. And so just today, I tried to pull this. I just Google, and this is Ford, who is looking for a FPGA design engineer for autonomous vehicle. So that's direct connection. You can see that, and you see many articles on that aspect. FPGA are a core aspect of autonomous vehicle. Why? Because you can reconfigure them. Okay, if you have an ASIC, you will need, if the car lasts for 5 years, how you can improve the software running on this ASIC? Where you will need to build an ASIC which is kind of generic, like a processor that will execute a program. If you are using FPGA, you can really use something which is very close to a hardware accelerator. Okay, so these were the 4 trends that I think are very important for the adoption of FPGA in our domain. And now some results. So you see that's the section about applicability. There are some success stories. There is a book that has been published, I think, 1 year ago about how to use FPGA in high-performance computing, and you see 3D FFTs, BLAST2 kernels, sparse matrix computation with better performance than CPU or GPU. So you can find these stories in this book. And that's probably very important for the community. But one aspect of it is that all of these success stories are using HDL, so hardware description language. So you need to have an expert in hardware to be able to, and in FPGA and the FPGA stack in order to be able to get this performance. You cannot get it from C, not a program that you write from C, okay? And that's a major point for our community. You cannot put that in the hand of our programmers. They don't want to be to develop a new expertise for hardware programming. So, as I mentioned, for JZip, some people have tried to use OpenCL. OpenCL has been provided by Altera since 1 year, and at least 1 year. And so people have been able to try OpenCL and try to build application and compare performance. And you have success story in image analysis, like edge detection, for example, where people compare VHDL development, or really programming at very low level, with OpenCL development. And again, it's much faster, and you can compare the performance. And they were happy with what they got. So that's kind of success story. Some other people have applied this for encryption And again, they got some very, very good results to encrypt some data streams. So, okay, it seems that there is a possibility to program FPGA with OpenCL. Now, let's go back to the story that I told you about JZip on the FPGA. Okay, so that's Altera, again, writing the OpenCL program and compiling it and generating the hardware configuration for an Altera FPGA. And they get very, very good performance, as I mentioned. And in fact, if you look at the comparison with Verilog, it was very compelling also. So this means that you don't need to invest in developing in low-level programming languages for FPGA. So that was a very, very compelling story. So after that, IBM, who was one of the comparison, or one of the performance comparison aspect of the paper, wrote a new version, a new Verilog version of JZip for the same FPGA and got a factor of 5 performance improvement. Okay, so which means that it's, programming in OpenCL is not really today a way to get the best performance for FPGA. How did they get very good performance with OpenCL? They really try to change the loops. So here you have a loop that just counts the number of characters that are the same in a string, okay? And just stop when the character starts changing, okay? So it's just counting the number of characters. And when they started the generation of this, they just took the C code and they generated something which is a very long string of adders to compute the addition of the lengths. And well, the performance was very low, really not compelling. So they decided to do the same thing to count the number of common character in these strings, but using an array and shifting bits or putting bits in order to count that. And that's what they do here. And the difference is that instead of generating a string of adder, they generate a tree of OR gates. Okay? How do you know that when you are a C programmer and you don't know the Altera chain? There is no way you can imagine that Altera chain will generate here a series of adder and here a trees of OR gates. How you can imagine that? Okay? So not only you need to have some skills in hardware, but also you need to know how the stack will behave. Okay? And so that's really showing that it's not ready for prime time. Okay? So there are some good news. It seems that the performance potential is there. It seems that the support market is there, but we have a problem with programming. OpenCL is not really ready for prime time. And so to give an example of that, I will show you the project that we started at Argonne. The objective of the project, so it's called Reform. The objective is to provide high-level synthesis from OpenMP4, so with the accelerator directive, and so call kernels that will be executed on FPGA, and do that at the OpenMP4 level, so not having OpenCL as the level of abstraction, but OpenMP4, and providing hardware optimization, so good performance, with no significant code change. So this means we don't want to do what they did in order to generate different hardware configuration. We really want that to be transparent for the user. And so this is the test bed we have. We have an ARIA 10 board. This is the processor or the server which is driving this card. And so since I told you about compression, what we try to do is to port the best compressor we know, which is Argonne SZ. This is a low C compressor for scientific data set. So we try to port it on the FPGA, the ARIA 10 FPGA, which is a high-end, state-of-the-art FPGA. And if you look to how this algorithm works, it has multiple steps, and we try to put all of them in the FPGA. Well, so the first thing to mention is that we didn't try to do any optimization, try to use in any way parallelism. It's just the host code calling a kernel which is supposed to implement this compressor. So the compressor itself is 1,000 lines of code. That's not a big code. It's a reasonable size code. And so, but you need to pay attention to certain things. You cannot have dynamic memory allocation. The compiler will not allow you that. You cannot use double pointer, so you need to rewrite the code. And then you have the code that has been generated, and yeah, we can run it in the emulator. Yes, we can run it. Okay, what does it mean? Well, it means that there is an OpenCL emulator that runs the code, but it has nothing to do with the FPGA. So you don't know if it really is working for the FPGA. So then you have to compile the thing, and it takes 80 minutes to go from OpenCL to Verilog. So you are not done. You have not generated the hardware. You just have converted from one language to another one, okay, to the hardware, the description language. Okay, and then boom, the compilation crash. And it crashed after several hours. So that's a problem also with FPGA. When you are generating a hardware configuration, it takes hours, and if it goes to the end, maybe it will run, but not at the speed you were expecting, or it will crash, and you don't know exactly why. Okay, so you have to look at the code. And then we discovered that we were trying to allocate memory inside the FPGA, or use local memory inside the FPGA, and this local array that we are trying to allocate, it was larger than the capacity, the memory capacity that you have in the FPGA. So we had to remove that part. So this means that if you look to the steps here, we removed this third step because we was not able to compile. Okay. Well, the code now is 500 lines. It took 5 hours to compile that, to generate the hardware. Well, it's running, so that's a good news. And it used 5% or let's say 12% of the total hardware resource available in the FPGA. Only 12%. So imagine now if you want to use 90% of how long it will take to generate the configuration for that. So it will take several days for very deep, very complex configuration. The other thing is that if you look at what SZ used, it's only 3% of the resources. A lot of resources have been used just to connect the FPGA to the host. Okay, some hardware resources are used for that. So that's not the frequency is 318. I was surprised. I was thinking that it would be 10 times lower than that. So I'm happy to see that it's not bad. So this started 2 weeks ago with several FPGA experts, people that are really in this domain, and we have not been able to run something very compelling in 2 weeks. Okay, and this is not a big program. This is 500 lines. Okay, so I think it will take a lot of time to port this compressor, and I think it will take some time for our community to be able to solve these two problems, bringing the abstraction level to OpenMP4 and generating transparently hardware configuration that are efficient. Okay, so that's I think the message for today. A funny thing to the end. So at the end of this talk, so this is Christopher Fenton, who put in 2010 a Cray 1. So the real Cray 1 that you have, if you look at the paper, you have the description of the Cray 1. So he put the Cray 1 in an FPGA, okay, and he was able to run it, okay, so that was very nice. And now he's working for the show for the Anton 2 machine. So there might be some connection here, I don't know, but...
Yeah, there are limitations on the number of times you can reuse the FPGA, so would you like to comment on that while we are testing the code?
No. You can, so to answer the question differently, now people are thinking of changing the configuration dynamically. So you are inside your application, and you are going from one phase to another. You can say, I will spend 2 milliseconds to reconfigure the FPGA in order to be more adapted to the next section. So you can really change the configuration as you wish. Yep.
Could you comment on double precision on FPGA?
I was waiting for this question. So you can already use today the DSPs and combine, I think it's 4 DSPs with the logic, and they will produce that automatically for you to have 64-bit arithmetic, so double precision. Okay, you can have it, but it's not as efficient as it could be if the DSP itself would be 64-bit. And so we had some conversation with Altera and Xilinx to understand if they would put that in the next generation after Stratix 10. And unfortunately, it's still, they have projects, they are developing things inside, but it's still not decided. So they don't know if they will put that. If the car market or the data center market ask for that, we will have it. If not, then